China teaching a Triz class, and I was told that one of the companies in China has developed a washing machine that doesn't use water. You put your clothes in it, and it increases the pressure, and it abruptly drops the pressure, and it causes the dirt to fly off the clothes with no water. So, awesome. Showing sunflower seeds. If I have seeds, cashews, walnuts, pecans, I need to shell them. I can use the same principle, increase the pressure very slowly, then abruptly drop the pressure, and the shells just crack open perfectly, and you can extract the nuts, the seeds. I was doing some consulting work for McCain in Wisconsin when I was with Duran, and they make French fries for like Wendy's or McDonald's. They take the skin off of potatoes. They put the potatoes in a large atmospheric chamber, increase the pressure, abruptly drop the pressure, the skin flies off the potatoes. That's how they take the skin off of the potatoes. Yesterday in the New Straits Times, there was an article, Pioneering New Technology for Food Processing. It says here, the technology developed by a French biotechnology institute and introduced into the local market involves a very short thermic treatment involving a fast pressure drop to a vacuum level, an innovative technology. So what they're saying is that they can separate the food from the moisture or the cooking oil with a rapid change in pressure, and then they can quickly prepare the snack for freeze drying or for storage. But it's the same principle. Now I'm using a very rapid pressure drop to separate the food from the cooking oil. So, you know, it's a big deal in the paper, but it's a simple application of a Triz operator. And it wouldn't surprise me if the French Institute used Triz, because the University of Strasbourg, like I said, is a master's program, and they're really popularizing Triz. So it wouldn't surprise me if that idea came from Triz. But what the modern Triz does, what Borsanella have done, and if I look at the Knowledge Wizard, the brainstorming software, is it's based on this type of a construct. And it starts with a physical contradiction. So I can work on the physical contradiction. When I start with the physical contradiction, I get separating in space and time and structure and on condition. And I say, okay, I want to work on the contradiction, separating in space. And I click on separating in space, and now I start to move into nested systems of operators. Here's 5 different ways of separating in space. And then in the more advanced software, I can click on each of those and come up with several ways of making those things. So what Boris and Alla have done is they restructured the theoretical basis of Triz to start with the physical contradiction, and then move into systems of operators that are organized around the laws and lines of how systems evolve over time. So you go through structured brainstorming by clicking here, then clicking there, then clicking here, and as you're clicking through that nested system of operators, you come up with more and more ideas. So it's a very structured brainstorming sequence. And the structured brainstorming sequence has 3 basic approaches to it. And the approaches are to work on the contradiction, resolve the contradiction. When I click on this, then I start with the 4 separation principles, and then for each of the separation principles there are systems of operators on how to make those happen. I can also say, how can I take the useful function and make it more useful? Or how can I take the function that's being harmed and make it less harmed or not harmed at all? So there's systems of operators here, system of operators here, and a system of operators here. And these are the basic leverage points for system change. So the most powerful is to work on, address the contradiction. And working on the contradiction takes more time, but you get higher level solutions. If I want to do something very quick and very fast and have just a few ideas, very quick and fast ideas at a lower level of solution, then I can try to take the function that's benefiting and make it benefit further, or take the function that's being harmed and make it less harmful. And there are systems of operators for that. So I can find a way to counteract harmful function. Here's I start to get into these operators. When I look at mismatch, I have 5 more ways of making that happen. And then there are examples. So I can brainstorm around these. So that's the way that the modern Triz software works. It works on the operators organized in systems based on laws and lines of evolution with a basic approach associated with working with the physical contradiction, or starting with the function that's benefiting or the function that's being harmed. So three basic approaches. And these approaches are in the brainstorming software. So the brainstorming software just has the operators that are used most of the time. So it's a good way to just start to train yourself and to practice using Triz. It's a good way to begin to crawl with Triz. The Knowledge Wizard and the Innovation Workbench, much more sophisticated for non-technical problems or technical problems, and they have all the known operators for the technical systems or the non-technical systems, using the same basic approaches, but in those softwares you create the system map, the software identifies for you the possible leverage points, and then you pick which ones you want to work on, and then you still have the same basic approaches. I'm either working with a physical contradiction, making a helpful function more helpful, or a harmful function less harmful, with systems of operators, but now I'm involving a lot more operators and can go into a much greater deal of depth.
Does this tricks replace altogether the mic, or it complement the some of the mic station?
Complement what?
The
DMAIC. Well, the thing with DMAIC is that DMAIC. If I take the 7 basic QC tools, histograms, cause and effect diagrams, check sheets, Pareto diagrams, flowcharts, SPC, scatter diagrams. When I look at define, measure, analyze, improve, and control, then I have strong or medium use of the tools. I've got all the tools apply or help me with defining the problem. A number of the tools are very strong for measure. All of these tools help me with analyze. And I get a lot of help from these tools in control. But when it comes to improve, all I've got is give me your ideas and I'll record them on a fishbone diagram. So if I look at the Six Sigma process, strong help in the front end, strong help in the weak end, but when it comes for ideas, we're very weak. But if I add Triz to the Six Sigma process, then I can take this, I have a method to help teams develop concepts, and I can make the whole system much stronger. So that's how I think that they complement each other. Okay, what I want to do before we go is just do a simple pluses and deltas for today. So some feedback on our class for today. We'll stop right here. And I want to know what are the things you liked and what can be improved for tomorrow. So give me some pluses and some deltas. What are things you liked about today? What could be improved?
Very fluid.
Pardon?
Very fluid in your presentation.
Very fluid. Okay.
Hey, the food.
Who said
Somebody's
that?
gonna say it. The big guy, the massive guy.
We like massive breaks.
Fancy. Yes.
What else did you like or could be improved? Big picture?
One the comment. You use the red pen a little bit as a because red pen people in the back can see.
Okay, can't see the red pen?
Yes. I just like how to.
Okay, we'll throw away red.
Sometimes you cannot see the letters slides.
Can't see letters in the slides.
It's quite far.
It's that.
Okay.
The software for only 90 days. The software, 3 months. Yeah. Try software is too short.
It should be 1 year and a half. At least.
That's data for us. Fast one for you.
Well, remember, this software is how Boris and Alla make livings so they can do more Triz research. Now, at the end of 3 months, you can purchase software or you can rent it. So when you need the software and you say, I want to use the software for a week, you can rent it from their website.
Oh, that's cool.
Other pluses and deltas?
What about renting you?
Yeah, you can rent me too. Other pluses or deltas?
A lot of examples, I think that's good.
Examples. Now for starting tomorrow, I want to get into Knowledge Wizard and Innovation Workbench. And what I want you to do tonight is I want you to think about what problems you would like to work on.
Any problem?
Any problem that's of interest to you. And tomorrow morning, I'll collect your ideas on things that you would like to work on, and we'll vote, and we'll pick maybe 3 of them, and we'll break up into 3 groups. Each group will work on a different problem. So that's how we'll do some class exercises with the software. Okay, so we'll do that. We'll work on some individual problems of interest for the next 2 days with either the Knowledge Wizard if it's a non-technical problem, or Innovation Workbench if it's a technical problem. So I'd like you to think about that tonight and bring those ideas in tomorrow morning. Okay, any other questions or comments? Okay, we'll see you tomorrow morning at 9 a.m.
Yeah, you can leave your workbook.
Three ways to increase solution ideality. One is the use of resources. So in Triz, understanding resources is very, very important because many times teams give up on a solution and say, oh, it's too hard to implement because they don't understand what resources are available. And so one thing a Triz master will do is they'll immediately try to get a thorough understanding of all the resources that are available either in the system, the super system, or the subsystems, because all those resources are available to you. And they're available essentially free because they're already in the system or the super system or the subsystem. So by understanding what resources we have, we can often implement a solution in a very neat way, and we can make a solution better. So Altshuler always strives to implement a solution at low cost by using resources that already exist in your system. The other thing that we need to talk about this morning that's also useful to improve ideality of a solution are laws and lines of system evolution. So we said yesterday that Altshuler discovered 4 things when he was looking at the patent database. And one thing that he discovered was he came up with a measuring scale for how innovative is a particular solution. Then he came up with a definition of an innovative problem or an innovative situation. And then we talked about his discovery of principles associated with the resolution of contradictions. And then the 4th thing that Altshuler found in the patent database were these laws and lines of evolution. So we want to talk about the laws and lines of evolution a bit this morning. And we can improve or enhance a solution also by using the laws and lines of evolution. And then the 3rd thing that Altshuler used to enhance solution ideality was the use of physical, chemical, geometrical databases. So this is also related to resources, but it's also related to the notion that when you get to higher levels of solution, you're often taking knowledge from one area and combining it with the knowledge from another area to produce a higher level solution. And so what Altshuler recognized is that he needed to make it easier for a person in one area to get knowledge from another area that they could utilize to come up with a higher level solution. So he had there is embedded in the innovation workbench databases of physical, chemical, and geometrical effects for your use to help you get some knowledge outside your own field in order to implement a better solution. So that exists in the innovation workbench. It doesn't really apply when you're talking about non-technical problems, but it does apply when we're talking about technical problems. So I want to talk about these things this morning, and then we'll go back in and look at the software, and I'll show you where these things fit into the software. First of all, let's talk about moving toward ideality with a fistful of resources. And we think about what kinds of resources are available to us in our system. And Morris and Alice say, well, we have a fistful of resources. We have functional resources, field resources, information resources, evolutionary ideas, substance resources, space resources, and time resources. So all those resources are readily available to us. And these resources can be visible or they can be hidden. The resources can be useful or they can be harmful to us. They could be harmful energy, harmful objects, and so on. They can involve a change of scale. They can be resources of change. We can combine resources. We can use resources with physical, chemical, and geometric effects. We can leverage resources with ideas, concepts, and systems. We can concentrate and accumulate resources. So here's an example. Let's take something very simple. We have a problem zone here, and in this problem zone we have a copper wire with voltage and current, and there's air. So what kinds of resources exist in this system? Okay, we've got the copper wire, we've got air, current, voltage, okay. Those are pretty obvious. Any other resources available to us? Well, if you asked the Triz master what kind of resources would be available to us in the system, they would start out like this. They would say, okay, we have the copper. We have the copper, but in the copper there's some contaminants in the copper, and they have a certain type and a certain amount. Maybe there's some silver, maybe there's some copper oxide, maybe there's other contaminants in the copper itself. You have some geometrical resources, so the diameter of the wire is a resource, the length of the wire is a resource, the shape of the wire is a resource. In terms of current, we have the amount of current, the form of the signal, is it AC or DC, the frequency of the signal. In terms of voltage, we have the amount of voltage, the form of the signal, the frequency of the voltage. In terms of air, air is composed of hydrogen, oxygen, nitrogen, carbon, temperature. And with the air, there's some pressure, there's some velocity, and there's some wind speed. When we're thinking about resources, then we want to be as detailed as possible in terms of what resources exist in our system. But it doesn't end there, because from some of these, we can derive other resources. So from the copper and the diameter and the length of the copper, we can get resistance. We can also combine several of these to create a magnetic field. We can take the copper, combine it with oxygen, hydrogen to get moisture. And that moisture can combine to form some oxidation. The oxygen and the carbon can form carbon monoxide and carbon dioxide. And moisture with temperature and speed can create cooling and dissipation. So if you were asking a Triz master what types of resources were available in the simple system, they would come up with a list that looks like this. So one of the things that we need to do is to train our minds to really understand what resources exist, not only in our system, but also in our super system and in our subsystems that we're interested in, because all of those resources are available to us. You can use existing resources in your system, super system, or subsystem, and combine them to derive other resources.
I see what the resources. That means you are able to manipulate and change.
Right. So here's an example of a problem that Boris Lotan worked on. In the late 1970s, a dozen fishing boats sunk in the North Sea during freezing storms. So you guys don't have to worry about freezing storms. But they have to worry about freezing storms. And so what happened is that ice would build up on the outside of the ship and form, very thick, maybe like 15 centimeters of ice, and quickly form on top of the ship. And then the ship becomes top heavy and turns over in the waves, and then sinks to the bottom. And the sailors would try to, in these ice storms, they would try to go out with sledgehammers and chip the ice off of the boat. But the ice builds up as fast as they can chip it. And so they need a resource to prevent icing. They need a large amount of heat. So where could there be a large amount of heat as a resource for them? Okay, there's the engine of the boat, which can provide some heat, but maybe not enough to melt all of this ice. Any other resource available to them? Well, one resource available to them was the seawater. So the seawater was, the seawater is not frozen. And so there's quite a bit of heat in the ocean itself. And so their solution was to use the bilge pump on the boat to continually spray seawater over the boat itself. They're using the heat in the ocean to melt ice. And so that was a resource that was open to them to prevent icing. Here's an example of a derived resource. In 1903, a steamship on a German polar expedition got stuck in the ice. They were 2 kilometers from open water. The sailors could not break through the ice even with the help of explosives. And the predicament was solved by using furnace ash, which the sailors poured onto the ice. The dark situation where they had a resource available to them, ash from their coal furnace, and they were able to take this ash, and with the solar energy, they were able to create some heat to melt half through the ice. So it's an example of a derived resource. There's also substance resources. So one of the things that the software will ask of us, if we're using Knowledge Wizard or if we're using Innovation Workbench, the software will ask us what resources are available to us, either in our system, our super system, or our subsystem. And there are help files in the software that say, think about substance resources. So any material from the system or its environment. So look for elements of the system, raw materials, products produced by the system, waste materials, inexpensive substances, such as water, air, sand, and snow. And the software will have an example for us. So it'll say exhaust gases from excavators and heavy trucks used in depots and pits are filtered using the extracted product, crushed rock, or cold sand. So the truck exhaust pipes are directed into the truck bed, and the filtering process takes place as the harmful contents accumulate on the rock. So snow, for example, is used as a filter in northern regions. So that's an example of using a substance resource to help improve the environment. There are field resources available to us. So field is any type of influence that an object can exert upon another. So mechanical energy, sound, oscillation, vibrations, thermal actions and interactions, chemical reactions, electrical energy, magnetic fields, actions and interactions, electromagnetic actions, light, and other types of radiation. So an example of a resource, the upward stream of air produced by convection from the heat of a lamp bulb can be used to rotate the shape of the lamp. So I think you may have seen effects like that. And there's also space resources, space in a system and its environment. Look for unoccupied space, space between elements, space inside elements, unoccupied surface of elements, space occupied by an unnecessary object, or space available in dimensions other than those already in use. As an example, storing boats vertically in a tall shed. Time resources, look for time before a process, time during a process, pauses, idling motions, the possibility of simultaneously performing several operations in post-process time. So here's an example that tankers that transport oil also are processing the oil as it's being transported. Informational resources, any kind of information about the current state of the system or its environment, information about variations of objects and processes of the system or its environment. Look for fields emitted from the system, substances leaving the system, properties of the system, or elements such as temperature, transparency, natural frequency, variation in flows or energy passing through the system or its elements. So an example, when cracks develop in a machine, low-intensity sound waves are generated while the machine is operating. These vibrations are a useful source of information. So special acoustic transducers can be installed that can be used to determine the defects and the probability of failure. And there's functional resources. Look for useful effects of additional useful functions, harmful functions taking place in the system that can be put to some beneficial use. So here's an example in software. Passengers of hijacked airplanes are exposed to great danger. In some cases, to prevent an airplane from being hijacked, its existing air circulation system can be fitted with a sleeping gas dispenser that can be activated. So we can also use the sleeping gas dispenser to measure sneaks. Financial resources. Investment, cash reserve, loans, bartering, other financial resources. Human resources. People. So if you're trying to develop a strategy, the human resources are very important. You know people who view this situation as a high priority, Where are these people at? What level? Other individuals or groups inside the company or outside the company, allies, subject matter experts, people capable of coming up with creative solutions, people who are capable of testing and implementing a solution. Are there ways to motivate people to improve the situation? So an example is Six Sigma, which uses project champions to help break down barriers associated with implementation of a project, provide resources. Other business assets, so think about equipment, facilities, inventory, information that could be available. So here's an example: exhaust gas from thermal power stations treated with alkaline chemicals to prevent pollution. The alkaline slag produced by burning coal at power stations is also a source of pollution. So by combining these two sources of pollution, they can neutralize each other. So that's a good example. The resources, it's very important for us to understand the resources and to utilize the resources that exist either in our system, supersystem, or our subsystem. Also, we have another method to help us improve idealities, the patterns of systems evolution. So we talked that this was something that Altshuler understood, and Altshuler found that the metrics associated with systems tended to develop according to S-shaped curves that look like this. And from these metrics of it, you can pretty much tell where your system is at in terms of its evolution. So stage 0 is a system does not yet exist, but important conditions for its emergence are developing. Stage 1, a new system appears because a high level of innovation begins to develop slowly. Stage 2 begins when society recognizes the value of the new system. There are lots of improvements. Stage 3 begins when the resources in which the original system is based are mostly exhausted. Stage 4 begins when a new system for the next generation emerges to replace the existing one. Stage 5 begins if the new system does not completely replace the old one, which has a limited application. So you can pretty much assess where your system is at in terms of its evolutionary life cycle and what's going to happen next in terms of your system and where that system is going. And then what happens is that systems tend to evolve in these series of S-shaped curves. So as one technological system becomes mature, then a new system develops to replace it. And the movement from one of these S-shaped curves to another is called a structural crisis. And so the Triz scientists like Boris Lotan loves history. And Boris, kind of like a superhuman individual, he reads like 2 books a day. And he will read books on history, and if he's working on a project, he'll go back and he'll study the history of that system, and he'll identify these structural crises that have occurred in the past in the system and how the system has evolved over time. And Altshuler found that the movement of one S-shaped curve to another wasn't random, but there were certain laws of evolution and certain lines of evolution inside those laws. So Altshuler found 8 basic patterns, and inside those patterns there were certain lines of evolution. And so some of the patterns of evolution that Altshuler found were the stages of evolution that we just talked about, that S-shaped curve, the evolution toward increased ideality. So remember, ideality is the sum of all the useful functions over the sum of all the harmful functions. That systems will tend to increase ideality over time. That systems, the elements of systems, develop in a non-uniform manner. There's evolution towards increased dynamism and controllability. There's increased complexity followed by increased simplification. There's evolution of matching and mismatching elements of the system. Evolution toward micro-level and increased use of fields, and evolution towards decreased human involvement. And then inside these laws of evolution, there are lines of evolution. There's a story about Altshuler one time where a group of folks came to him and they made plate glass windows. And they had a problem with their plate glass windows. It was a continuous casting process. And they would cool the plate glass on rollers. And the plate glass would tend to sag a bit between the rollers, and so their glass was slightly wavy. And so they came to Altshuler and they asked him if he had any ideas associated with that. And Altshuler thought about it, and he began to think in terms of these laws and lines of evolution, and he was thinking in terms of increasing towards micro level. And Altshuler said, well, what you really want is, he was thinking, what you really want is you want to take the rollers and make them smaller and smaller and closer together. And then he thought, what better roller could you have than a molecule? Why not use molecules as rollers? And so he suggested to them, why don't you take a low temperature melting metal and then use the molecules of the metal as rollers, and the rollers will be so small and they'll be so close together you won't have to worry about any waviness in your glass. And they said, thank you very much, it's a mistake that we came to see you, don't call us, we'll call you, forget this ever happened. And they left. And then 5 years later, there was a company in England that came up with the float glass method of making plate glass. That exactly did what Altshuler had suggested from this law of evolution. And so they came back to him and said, well, maybe you're not so crazy after all. What other ideas do you have? But you can use these patterns of evolution, and inside these laws, I think Boris and Allah have discovered 10 laws of evolution, and they have 400 lines inside these laws of evolution from their research. Here's an example of one of the laws of evolution, that systems will tend to become more dynamic over time. So you'll start out with something and it's immobile, and then when you have something immobile, someone will come and add a hinge. And then there will be multiple hinges, and then it will move to something completely flexible. Then it will develop into using a liquid or a gas, and then finally develop into a field. So in terms of a physical system becoming more dynamic, this would be, the dynamic would be the law of evolution, and then these would be lines inside that law. So an example could be if you have something immobile like a knife, someone adds a hinge, you get scissors. You add multiple joints to make something completely flexible, you get a wire that can be used to cut cheese. Then you move to a liquid or a gas, and you have a water jet that can be used to cut metal. And then you move to a field, you use a laser beam as a cutter. And you can also see it in steering systems. You start out with something very simple, like a direct mechanical linkage for Ford Model T. Then you go to mechanical assist, a steering gear with a ratio in it. Then you move to something with a liquid, a hydraulic steering system, and then something with a field, an electronic steering system. Or in measuring, you can go from a ruler to a folding ruler to a tape measure to ultrasound to a laser measure. And we mentioned before that there is software that Boris and Allah have come up with for assessing intellectual property. So what they do is they pick the laws and lines of evolution that are relevant to that system. They also take some of the operators that are some of the most used operators, and they take a look at a current patent and they say, how much of the evolutionary space is this patent occupying? And so they look at these specific laws of evolution, and they look at lines inside these laws, and they estimate that this patent is occupying, this amount of evolutionary space. And so then they say, well, let's brainstorm, and see if we can't, from guided brainstorming, come up with a new idea that uses more of this evolutionary space. And so they come up with a new development that uses this much of the evolutionary space, and then they patent that and supersede, the previous patent. But still, there's more room for the system to become more dynamic, and more matching and mismatching of components, and more use of resources, or more resolution of contradictions and so on. So there's more developments that can still occur in that system. Another way of improving the ideality of a solution, so we talked about 3 ways. One is increased use of resources will improve ideality. Another way to improve ideality is going to be utilizing laws and lines of evolution, because if a system is going to evolve that way and your solution accelerates that evolution, then you will have a better solution moving along laws and lines of evolution. A third way is to use physical, chemical, and geometric effects to increase ideality. So often a complex system can be replaced with a simpler one if an appropriate physical, chemical, or other effect is used. So in manufacturing of pre-stressed concrete slabs, reinforcing rods must be stretched. Instead of using a complex hydraulic device, the rods are heated and expand by themselves. That's an example. So in the ideation innovation workbench software, there's a database of physical effects, chemical effects, and geometrical effects to help. If you understand that you need something in your system to perform a particular function, then you can go over those physical, chemical, and geometrical databases and see if you can find a physical, chemical, or geometrical effect that will do what it is you need to have done in your system. Or if you have something being done in your system but it's too complex, maybe you can use one of these effects to make it simpler. Maybe reduce cost to make it simpler. Okay, so let's go look at software now. And when we were using the brainstorming software yesterday, let's look at the brainstorming software first. If we're using the brainstorming software, we define the problem. And so yesterday we worked on defining the problem by looking at the supersystem, the subsystem, the system, what happens before and afterwards, inputs, outputs, causes, and effects. Then you formulate a task, and you, in the brainstorming software, you try to find patterns like this in your system, where you've got a physical contradiction where you want something to happen because something useful happens in your system, but you don't want it to happen because something harmful happens in your system. And then you can brainstorm around systems of operators to resolve the contradiction, find a way to counteract the harmful function, or find a way to modify it or make the useful function more useful. So you come up with as many ideas as you can from steps 1 and 2. And then in step 3, you combine the ideas into concepts. So you might have 2 or 3 or 4 ideas that you can combine together and create even a stronger idea. So you can combine ideas into concepts. Then you consider resources to increase ideality. So here's our checklist. Are there functional resources, field resources, information resources, substance resources, space resources, or time resources that we can use to increase ideality of our solutions? And then we prioritize our solutions, pick a solution for implementation, and then we say, okay, what subsequent tasks need to be addressed, and now can we use Triz to work on those subsequent tasks? So that's the very simple flow that's in the ideation brainstorming process. And actually, this brainstorming software is pretty inexpensive, but it has some really good operators in it. And just using it helps you to train your mind to think in the way that Boris Lotan thinks when he approaches problems, training your mind for further work in Triz. Let's take a look now at the Innovation Workbench software. So if we can pull up Innovation Workbench software. And Today and tomorrow, what I want us to do is focus in on Innovation Workbench and the Knowledge Wizard software, and whether we're working on a technical or non-technical problem, we'll use both, because the Innovation Workbench software has recently been updated. So when we're looking at the Innovation Workbench software, we're seeing the latest thinking from Boris and Alla and their team. The Knowledge Wizard software is in the process of undergoing a huge revision. So it will look more like the Innovation Workbench software. And the new version is just about ready to come out. So probably in the next couple months it will come out. So I want you to be familiar with the Innovation Workbench, the look and the feel of it, even if you're going to use Triz for non-technical purposes, because the new edition of the Knowledge Wizard will look a lot like the Innovation Workbench does in terms of its structure when they finish the major revisions to it. So let's look at the top of the software package itself. There's a light bulb at the top. And when you click that light bulb, you get a screen that looks very much like the screen that was in the brainstorming software. So again, when you're using this software and you're working with a team, anytime anyone on your team comes up with any idea at any stage of this process, you immediately write that idea down. And so you click the light bulb, you type in the new idea, and you save it. And it'll even, the software, we talked about this a little bit yesterday, where you're at in terms of the process is on the left-hand side. Where you're at in the process, your ideas get recorded at that, so idea number 1 came before we even started. Okay. But anytime you have an idea, you're encouraged to click on the light bulb and write it down. There's a report function like there is with the brainstorming software. So on the left-hand side of this software, we're going to be typing a lot of information into it. We'll be answering these questions, and we'll be coming up with ideas, and we'll be working on this left-hand side. The right-hand side gives us instructions of how to do the left-hand side. When we're finished typing and all of our ideas are in here, we can click on Report, and then it will generate a Word document that you can immediately print out or take to a meeting. And you'll have all of your ideas recorded there, as well as all of the notes you took during discussion as you were working through this process. The next thing over is the contradiction table. So Boris and Alla do not encourage us to use the contradiction table because it's very old. It's the first thing that Altshuler did, and it's just not as useful as the systems of operators and the more advanced work in Triz. But if you want to go back and use Altshuler's basic contradiction table, you can. So you can say, you know, what are the 2 aspects of the technical contradiction? So maybe it's speed, and maybe it's volume, or maybe it's stability. And then here is the innovation principles, replacement of a mechanical system. Then there's an explanation of the principle on the right-hand side, homogeneity, segmentation, mechanical vibration. And there's an explanation of the principle with some examples on the right-hand side. So you can use Altshuler's matrix if you want to, although Boris and Alla don't really recommend it so much, because even though people find it useful, it's not as useful as the more recent Triz technology. The software can be customized. So you can create a customized index, and you can also add examples. So if you are using the software and you're developing your own applications of Triz, you can develop your own database. Then, like there was in brainstorming, there's a lot of e-learning associated with Triz itself. So if you want to know about Altshuler's levels of inventions, you can come here and look at the levels of inventions. or if you want to know about contradictions, here's an explanation of contradictions. Resources, here's a fistful of resources, and so on. There's a help file, and there's also a tool bench. So this tool bench you'll find both in Innovation Workbench and in Knowledge Wizard. And you'll notice it says Ideation Tools and Applications. So if you want to work with the system of operators, then so if I want to go in and just get a few quick ideas, I don't want to go through the whole Triz process, but I just want to come in and start using some operators and get some quick ideas. Then I can go directly into the system of operators, and they say, okay, here are some universal operators that are applicable to any situation. So I can click on those and I can start brainstorming around these operators that are applicable to any situation. Here are general operators. So here are operators to resolve a contradiction, eliminate a harmful function, or increase a useful function, increase the effectiveness of a system, synthesize a new system. So maybe I want to increase the effectiveness of a system. How can I do that? And now I can start to brainstorm around ways to increase the effectiveness of a system. Here's the innovation guide. So I can create or modify a resource. I can transform a resource. Here are frequently used resources. How to find a resource. So here's how to find or create a resource. How to utilize an available resource. Again, these are aimed at technological systems. The Knowledge Wizard would be aimed at non-technical systems. And then here's a knowledge index. So I need to find out some more information about vibration and waves. So I can go in here and here's some information on vibration, standing waves, resonance, elastic waves. Maybe I want to know about vibration. Here's some information about vibration and some uses for it, or some phenomena accompanying it. Here's the contradiction table. Again, Altshuler's original 40 principles, if we're interested in looking at those. Very simplified Triz algorithm. So Altshuler had a Triz algorithm for inventive problem solving. Now I can also go into the software and I can just do some quick things with it. So if I want to improve a product or a process, then here I can start to say, what do I want to do? I want to improve a product feature, a process feature. Do I want to improve a measurement or a control system? Do I want to simplify a product or a process? So if I want to do this, then I can now start to brainstorm around systems of operators to reduce complexity. So I can look at these, see an example of it, see a number of examples of it if they're available, and then just start to come up with ideas. So when I come up with an idea, I click on the light bulb and record it in. Anybody want to improve reliability? You can improve a harmful function. Here's some operators for that. Eliminate a harmful function. Improve a useful function. Eliminate a harmful function. Synthesize a new system. Maybe develop a system for measurement. So if I want to work in measurement, here are some systems of operators to work on direct ways of improving measurement and control. So I can click on those and see some examples. Here's express failure analysis, a little bit of anticipatory failure determination, very light. Express failure prediction. Pardon? Yeah, there's a whole other software package, but this gives you just a little bit of it. Or if I want to utilize more resources, then here's the different types of resources that I can think about. So there's also, to work work on subsequent tasks. If I have an idea I want to implement, but I've got some subsequent tasks to work on, and I see this that looks very much like the brainstorming software. And then here's the innovation guide, so if I need to use the innovation guide, it's available to me, or the knowledge index. So those things are directly applicable. So if you want to, you can go and do just very quick things with the software itself. When you're working on a project with a team, then what you want to do is you want to just follow step by step the steps that are on the left-hand side. So you want to first of all state your project objectives, and you want to answer these questions, the importance of the situation. Then get into the innovation situation questionnaire, brief description of the situation, detailed description of the situation. Now you see the same kinds of things that we looked at in the brainstorming software. We can also think about here, looking at the super system, the system, and the subsystem, defining the system name, the system structure, the super system and the environment, systems with similar problems. So we can go and look at this, and then we can read on the right-hand side, and then you can just type in information. And if you come up with an idea, click on the light bulb and add your idea.
So this is the same ideation process you saw in the website software.
Yeah, but just in more detail and with more operators and more information available.
And it also depends on the user organization, whether they want to use the ideation to fit the software, or possibly combining with manual tools and software.
That's true.
Because it allows you to go in at any point of time during the ideation process.
That's right.
Now, talking about the software practically, if you have a group of scientists, probably you just like one person to take down notes on the ideation process.
What I usually do when I'm working with a team is we'll project the software up on a screen. And then we'll have a team like we have here. And the size of the team depends on the problem you're working with, because you want a true cross-functional representation. And then you'll just project it up, and you'll work right with it from the software itself.
What if after the session, everybody goes back to their apartments? Is the software shareable, or is it a user system that runs at the server base?
You can put the software on a network if you want to,
So it's network.
or it can be on a standalone PC or whatever. And you can also print out, do the report function in Word, and then email everybody the Word copies. And there's two ways that I've done this when I was at Ford. One is that I could work on a team with a project and say every Tuesday at 2 o'clock, come and meet in this room. And then we just work on it for an hour or two every Tuesday at 2 o'clock until we're done. Or you could gather a cross-functional team, and they may be from remote locations all over the world, and you come together for an intensive 2 or 3 day session. And believe me, by the end of the second or the third day, and you've been doing all this thinking, the team's exhausted, but usually you come up with maybe 60 or 70 ideas, of which maybe 10% of those are actionable, and the team's really excited about it. So the first step is to pick a problem to work on, and then follow the steps in the innovation situation questionnaire. And whether our problem is technical or non-technical, I'd like us to use the innovation situation questionnaire that currently exists in the Innovation Workbench software, because the Knowledge Wizard is being updated. So this is the Knowledge Wizard questions. They're very similar, but they're slightly different in terms of the explanation and in terms of their order. So this is what Boris and Alla are thinking now. And the new Knowledge Wizard will have the same innovation situation questionnaire in the same order. So we might as well get used to the one in Innovation Workbench. So the first step is to answer these questions. And as we're answering those questions, if we come up with ideas, click the light bulb and then put the ideas into the software.